Hi, welcome to the International Space Station Flight Control Room. This is where it takes place. I am here today with Al Drew. He's the astronaut. He is also the Habitat Demonstration Unit Project Lead for the Advanced Exploration Systems Program. He's here with us to talk and connect with the Distance Learning Network, and we're going to be talking with some students at the Zion Lutheran School. Al, first, let's just go ahead and briefly just give a brief discussion, so everyone knows what it is that you do. Explain a little about what you do as the Habitat Demonstration Unit Project Lead.
Okay. The main thing is that we're looking at interplanetary and deep space exploration. And these are going to be marked by very long missions, very deep, far off into space, and quite frankly, you need a place to live and work. And so we work on the places where people do their normal things that you might find on a space station or a space shuttle, and also where people would live, where you sleep, where you eat, where you just play a game of cards or hang out and watch the world go by.
Really quickly, how is deep space different than what we're doing now?
Deep space is different for one in that you're very far away from Earth, so now if we have a problem on a space station today, we can be on the ground within hours. If you're halfway to Mars, it may take you months before you get back, even if something goes wrong. The other big thing is that radiation in deep space. The Earth has a magnetic field around it that deflects a lot of really just bad amounts of radiation that are not far above us. Once we get what we call the Van Allen belts, you are out in the deep space radiation. Galactic cosmic radiation is what it's called, and you wouldn't live very long out there unless there's a lot of shielding around you. So that's one of our big challenges, is to figure out how much shielding to put around these vehicles in places where people live while we're out there in space. Another part is that I learned when I was on the job was that it's much, much colder out there in deep space than it is right even where the International Space Station is. The Earth is a very big, very hot rock that keeps us warm. These are our spacecraft warm to some degree when it's next to it. The further you get away from the Earth, the less warming you get from that, even though the moon has the ability to warm you up. So when you're in deep space, keeping things warm and operating temperature is a much tougher challenge.
Okay, thank you. So with that, for that quick description. So with that, let's go ahead and connect to the Distance Learning Network. Ryan, are you there?
I am, and Zion Lutheran is with us as well. They are, I'm sure, happy to begin questions now.
Great. Well, we're ready. Let's start.
What is the best rocket that can go to Mars right now?
Okay, so that question is, what is the best rocket that can go to Mars?
What is the best
Yes.
rocket that can go to Mars? The best rocket that can go to Mars is one that is the most fuel efficient. Currently, the big problem we have with going to Mars is that for every pound of anything we take to Mars, be it you or your luggage or your food or your clothes, we need 1,000 pounds of fuel. And that adds up very, very quickly, and especially if you're launching all that to orbit at maybe $50,000 a pound. So we need things that are much more efficient than our current chemical rockets. And the best fuel is a fuel that is light. So electrons, quite frankly, is the best thing to use as exhaust from your rocket. Now we can either get that by way of nuclear sources. So if you have a nuclear reactor, it can spit out. That is the exhaust, like Franklin Chang Diaz's Vasimer rocket engine. Or you can actually use sunlight. We have these solar electric propulsion motors that we're working on right now, where you take solar arrays like you find on the space station and you convert that into thrust. And quite frankly, that's free fuel. I mean, you're using the sun to power yourself around the solar system.
Okay, we'll take another question.
How much capacity can the average rocket hold?
How much capacity can the average rocket hold?
How much capacity can the average rocket hold? Boy, that depends on the rocket. I believe the space shuttle, please don't quote me, could take about 60 tons of mass to orbit over and above itself. Our current commercial rockets are somewhere closer to maybe 20 tons of mass that they can take to orbit. NASA's working on a rocket right now that they want to be able to take 130 tons of mass to orbit, and when we do that, then we'll be able to do good interplanetary missions.
Do we have another question?
What would be the effects of heating a Mars polar ice cap, and would it make the climate or temperature change?
And let's repeat that question one more time, please.
What would be the effects of heating a Mars polar ice cap, and would that make the climate change?
What would be the effect of heating the Mars polar ice caps, and would that cause the climate to change on Mars? That's a really profound question. Yes, much of what Mars's ice caps are frozen carbon dioxide, so it's dry ice. And so if you were to liberate all of that carbon dioxide in the atmosphere, I imagine it would have to have some effect on the atmosphere. You'd have a greenhouse effect. One of the problems we have with Mars' atmosphere is they have had the reverse greenhouse effect that Venus has had, in that they don't have enough carbon dioxide, and so Mars is much colder than the Earth would be if it was out there at Mars's orbiting radius. So I'd imagine it would warm up Mars a little bit, which might make it a more habitable place.
We're ready for the next one.
How do you recycle water on the space station? Like, what's the process of that?
How do we recycle water on the space station? That's also a very good question, because every drop of water we get on the space station has to be imported. We make none of our own. So we have means of, on the Russian side, of basically distilling that water and bringing it back through their different processors. The United States has brought up some of their own water processing equipment, most famously the urine processor, to be able to take our own urine and process that back again, distilling it and turning it back into usable, potable water.
In the movies, they always have like dome-shaped houses on like Mars. So I was wondering, if we wanted to make a colonization on Mars, would that like be scientifically possible? And if it would that protect us from the constant sandstorms and rain?
Okay. The domes you see on planets in books and movies, they're really nice, and that might be a place you might enter and exit where you live if you were on Mars. But as a good friend of mine, Christopher Stott, once mentioned to me, says like the same thing with the Moon and Mars. You would not live on the surface of either of these planets. You would live in those planets beneath the surface, because the ground around you would have to protect you from the radiation, which would be much more of a problem for you than the sandstorms and winds you'd find on the surface of Mars. Now understand, the air at the surface of Mars is very thin, almost like what you'd find up at 100,000 feet above the Earth. So even though it looks very dramatic to see the the dust devils and winds out there, it's really not that powerful in terms of its force like you'd find here on Earth. But the radiation would be a much bigger problem.
I was wondering, is it like hard to adjust to the life in space?
Is it hard to adjust to life in space? You do have to make some adjustment to it. It usually takes a couple of days before you get through just the basic part of it, just getting used to the fact that there is no up, that your sunrises and sunsets come every 45 minutes apart, and you lose, for me, I lose a good sense of what time it is. Without my watches and clocks around me, I'd be completely lost. I'd be trying to radio friends and people like that from space at all times of day and night, and annoying them. So, and the last thing you should get used to is just being spastic. On Earth, you're hauling your weight around, and in space, all you're hauling around is your mass. And so you don't need your big muscles like quadriceps and biceps and things like that to move around. You use your fingertips and your toes to push yourself around gracefully. And for the first few days, when you are pushing off with your big muscles, you take off too quickly and you knock things off the wall, and people recognize that you're a rookie.
What kind of meals do you eat on the space station?
What kind of meals do we eat? Almost anything you could imagine having here on Earth. We have a food laboratory here at Johnson Space Center that's been working continuously since we've had a space program on making really delicious food that's nutritious for us. And they've let their imaginations just run wild. I've had all kinds of Cajun food like etouffee and jambalaya. I've had spaghetti. I've had steak. I've had shrimp cocktail. The only things we really try to avoid are things that are crumbly, like popcorn or crackers, because once you bite into them, the crumbs don't just fall to the floor. They float around and get in people's eyes and hair, and that gets to be annoying.
What is the best energy power to go to Mars? Nuclear, wind, or solar?
Did you say nuclear, wind, or solar?
nuclear power, wind, or solar power?
Okay. Well, wind power, I'm assuming you mean the solar wind using the pressure from the sun, because otherwise there's no air in space to take you out to Mars. So you can put out big solar cells, but they'd have to be very big, more than a kilometer across, to give you some of the thrust. Solar power is what I talked about. When you take your solar radiation, you pick it up with a solar cell, and you convert that into thrust. And nuclear power simply takes the same thing. Rather than using solar energy, you're using a nuclear source. Now, aside from the problems you have with a nuclear source, the radiation and all the shielding you have to have, if you're going to go out much past Mars in the solar system, you probably need to have nuclear power, because the power of the sun's light drops off with the square of the distance. So going twice the distance from the Earth as you are right now, the power of the sunlight is now 1/4 of what it would be. Going 3 times would give you 1/9. So going out to Jupiter, which is about 9 times the distance from the sun as the Earth, you would have only 1/81st, or about an 80th, of the solar power that you have here near the Earth. And so you can imagine something like having the solar arrays on the space station, which is an acre of solar arrays. You would need 80 acres of solar arrays to get the same amount of power out of it. So once you get past Mars, which has about half the amount of sunlight that we get because of its distance, you really need to go get the nuclear power, simply because the size of the solar arrays to get that energy gets to be just ridiculous. And the same thing for solar wind too, because that solar wind would drop off as well as you got very far away from the sun.
What new technology do you see for space travel to Mars?
Oh, lots of new technologies out there. A lot. So we talked about these solar, electric, and nuclear and power engines. Those are new technologies that we really don't have right now. We do have ion engines, but they're very, very low in power. We put very small satellites out in deep space with them, and your breath, if you're just blowing against your hand, will put out more thrust in those engines. We're looking at things that put out real rocket-type thrust. Those are much bigger technologies there. The other part is automation. Sitting in mission control, where we can control just about every aspect of the space station. We can determine its attitude, its altitude, the life support systems, all in very much real time. We have cameras that look over the astronauts' shoulders as they work aboard the space station. If you're near Mars, light can take up to 20 minutes to get back to Earth from where you are at Mars, and another 20 minutes for you to go do a change from what you see. And so we need to have automated systems, almost like you take a mission control and all the brains and the ability that it has, and try and put that in a box. Make an artificial intelligence system that'll let us make those type of decisions that mission control can make, and keep astronauts out of trouble, because it's a lot of information, and it's more than probably 4 people could handle. We have rooms and rooms of very smart people here in mission control who look at all these different just streams of data coming back from the space station. We won't have that luxury out by Mars, and so we need better computers, smarter computers that can handle that. There's this. I go through just pages and pages of new technologies that I'm poring over every day to see how they can help me get things like deep space habitats out by Mars late in the next decade.
Great questions. Do we have any more?
What is the best way to transport the most oxygen?
What is the best way to transport the most oxygen? It depends on what you're trying to do. If you just want to get it into as small a volume as possible, then liquid oxygen is a very good way to do that, and we've done that on airplanes and spacecraft for a very long time. However, you need to keep it very cold, and that takes a lot of power. It can also be very dangerous. Liquid oxygen, when it mixes with things, can be explosive from time to time, and so you want to find ways to keep oxygen from being dangerous. Well, then you can tie it up in different types of compounds. I'm not sure what different ones, like there's metals like lithium and other ones that you can bind up the oxygen. It's not quite as dense as liquid oxygen, but it's very close. And then you can heat those things up or have a catalytic reaction and release those. In fact, a lot of the new aircraft you'll see out there flying around now have what are called onboard oxygen generating systems, or OBOGs. And that's exactly what it does. It takes oxygen that's bound up in a compound with a metal, and you can heat up and release that oxygen, and then it comes back out that way. And so it just depends on what application you're using it for and what you're trying to achieve.
What are some of the biggest problems about colonizing Mars?
The big problems for colonizing Mars is that you need a way to support that colony on Mars. So you're going to have to export, or if you're there, import all of your food, all of your water, all of your air, everything you need to live. Then you're going to need a wagon train of ships going out to Mars, burning rocket fuel by the truckload to get out there to support everything. And if one of those doesn't make it for some reason, you could be in for a very lean time between those resupply missions. So big thing is you want to be able to grow your own food or create your own food while you're there. Mars, we suspect, will have seen evidence that there's water beneath the soil. So if you can use your own water there, you don't have to bring that up from Earth as well. And that's probably the key ingredient to life is water, because you can actually turn water into air that you can breathe. So we need ways of harvesting that water and then using it to keep ourselves alive on Mars. Also, Mars has a lot of the same raw materials that Earth has. So if you're going to, rather than bring up some type of iron, bracket or something like that, you might be able to manufacture it there at Mars. It'd be a whole lot cheaper and easier. And with things like 3D printing technology now, we may be able to create complex pieces of equipment without having to go through a big factory. You can sit there and make a 3D CAD file of it and then print it up and use it there. So it's that ability to be self-reliant, so you're not so dependent upon this wagon train of logistics from planet Earth to keep you alive, will be the key to us colonizing Mars.
What type of spacecraft will be needed to land on Mars, and would rockets still work?
To go land on Mars, I think you'd almost have to use a rocket unless we develop something very new and exotic. These nuclear propulsion systems and other ones, they don't put out a whole lot of thrust for their weight. They're very, very efficient. And so if you want something that puts out a lot of power, that dragster of a motor, then you need just a chemical rocket to get you in and out of Mars's atmosphere. So I expect we'll use a combination of aerodynamic braking, parachutes, and then finally just a landing rocket to get us those last few feet down to the surface of Mars. And you're going to need a rocket to get yourself off the surface of Mars. That's one thing we've yet to do, is have something land on Mars and take back off again. So that's where you're going to need a chemical rocket. You can't just get there by bouncing bags or parachutes. If you want to get off the surface of Mars and come back to Earth, which I would like to do, then you'll need a rocket. And a chemical rocket is about the best solution for that.
So great questions, and we still have time for a few more. You got any more questions?
What would be the best plant to grow on Mars?
The best plants to grow on Mars? Was that the question?
Yes, sir.
Okay. Boy, I really couldn't tell you, but I imagine that...
Maybe we should ask you what's your favorite vegetable.
What my favorite vegetable is? Let's see. Like anything that makes a good salad. Give me lettuce and tomatoes and fruits like oranges and apples. But there's probably more efficient things out there that like soy that you can turn into lots of other foods if you're going to grow something like that, or things that don't take up a whole lot of nutrients or a lot of resupply to give you what you need. But I'm not the person to ask about that. I'm a physical scientist, not a biological scientist, and I'm profoundly ignorant about those things. We do grow things in our habitat demonstration units, fresh vegetables like cucumbers and cherry tomatoes, and it's always good when you get to harvest your own garden to put on your meals, though. So it's more than just nutrition. There's a certain part of it it just feels good.
In space, what is the average miles per hour at top speed?
Okay. To get to orbit and stay in Earth orbit so you don't fall back to Earth, you must go at least 17,500 miles an hour. Now, ironically enough, that's at the altitude of the space station. If you were to go out and measure the speed of the moon, it would actually be much slower than that. It doesn't fall to Earth. So the further you get away from the Earth, the slower you can go, but you still need that much speed to get out there. The Apollo rockets that went to the moon left the Earth's atmosphere going about, Mach 32, which I think is somewhere in around 25,000 miles an hour, much faster than orbital velocity, but they were going much slower when they got out to the moon. Imagine if you were in a roller coaster, at the very bottom of that roller coaster, to get to the top of that, you need a whole lot of speed, but once you're at the very top of that hump there on a roller coaster, you're almost out of speed. And that's like going to the moon. You leave the Earth with a lot of speed, but you lose a lot of that energy on the way up to the moon, so you're not going very fast by the time you get there. So we always talk about it's called delta V, or the velocity you need to escape to go other places, and I'd say it's I want to say 32,000 feet per second, and I haven't quite figured out how to convert that to miles an hour for you on the fly here yet. But that's about what you need to escape from the Earth.
Great. And thank you. I think that's all the time that we have now. Al, thanks again for coming out and talking with the students at the Zion Lutheran School. Back to you, Ryan.